Welcome back. In this lecture, we look at what are called planar graphs. Planar graphs play a very important role in graph theory, especially in dealing with complex problems where many other uh, techniques fail on general graphs. We try to look at special class of graphs, and one of the most important classes of graphs that comes into mind is that of planar graphs. So what are planar graphs? If you look at graphs, when you think about it, one of the things that you always think about is the representation of the graph as vertices and edges that are mapped onto the plane. Now, when we draw a graph on the plane, it often happens that you need to draw the edges such that the edges cross each other. But if it is possible to draw such a way that the edges does not cross, then it's much easier to visualize. And therefore, one would like to see if it is possible to draw a given graph on the plane without the edges being crossed. So what we want to do is to see under what conditions we can have this property, and what can you say about such graphs? Do they have some specific structure, and questions related to that. This is what comes under the study of planar graphs. Okay, so let me define what a planar graph is more formally. A graph is said to be embedded on a surface. Okay, so the surface can be the plane, or it can be other surfaces like torus or higher genus surfaces. A graph is said to be embedded on a surface if you can map the vertices of the graph to distinct points on the surface and the edges of this graph to simple curves, okay, between the corresponding points, so that no two curves intersect except at their endpoint. This is what we mean by saying that it is not crossing. So when I say simple curve, these are actually more technical terms, which I don't want to go into the details. But for the time being, just take it for granted that when I say a curve is simple curve, that it's a curve which does not intersect itself. So take simple curves between the corresponding points, and we don't want no two curves to intersect except at the vertices where they have their endpoints. If such an drawing is possible, then we say this is an embedding of the graph on that surface. Now, if this particular surface happen to be the plane R2, then we say the graph is planar. Okay, so a graph that admits an embedding on the plane is called a planar. So here are some examples. So the first graph that you see here is a graph on 6 vertices, and you have 1, 2, 3, 4, 5, 6, 7, 8 edges, right? So you have this this graph. And then and you can very well see that this graph is represented on the plane where you have the vertices as distinct points, and whenever you have an edge between a pair of vertices, then you draw a line segment connecting them. And this has the property that the line segments does not intersect anywhere except at the vertices. Similarly, the second graph, you can see again as a collection of points and lines such that and curves such that they don't intersect each other. So therefore, we can say that this is also a planar graph. Now, a graph can be a planar graph even though its representation that we draw on the plane is not satisfying this embedding property, right? For example, what we are saying is that a graph is planar if it admits an embedding, right? So the definition of the planar graph does not say that your embedding needs to be planar embedding for the graph to be planar, right? Only that it has at least one embedding where it is planar. So to see the difference, let us look at this graph, which is a complete graph on 4 vertices. Right? You have this first embedding, right, where the edges actually intersect each other. Right? Therefore, this is not a planar embedding, but the graph is planar. You have this planar graph, which whose embedding, the given embedding is not a planar embedding, right? It's not an embedding on the plane. But the graph is planar because it admits a plane embedding, right? So if you look at the second picture, it's the same graph with a different embedding, which is also an embedding on the plane. Now, consider this embedding of the graph, right? The second embedding, right? Which is an embedding on the plane. Now, an embedding together with the graph together with an embedding is called a plane graph. Right? So, embedding of a particular embedding of a graph is if it is on the plane, then we say the graph is a plane graph. The planar graph together with an embedding is called a plane graph. So the second embedding, we say it is a plane graph because it comes with the embedding. Where the first embedding, first drawing, right? So you cannot say it's an embedding on the plane, right? So the first drawing is not an embedding. Therefore, the graph is planar, but it is not a planar embedding. Right? So therefore, we don't say it's a plane graph. It is a planar graph. Now, let us look at an example on R2. Right? Consider a plane graph on R2. Now, if you look at such a representation, you will see that intuitively speaking, you will see that if you look at any cycle, right? If you take any cycle in the graph has cycles, then the cycle basically forms a kind of closed curve, right? Now, if there is a closed curve on the plane R2, then this closed curve basically separates the region, right, or the plane into two parts, right? The region into two parts. One is the inside part of the curve, and one is the outside part of the curve. Now, this again is intuitively clear, but to prove this is not exactly simple. So we will not go into it. This can be studied in another different course. But this is a very famous result called Jordan curve theorem. Okay? So, what is the Jordan curve theorem saying? Right? So, if you take any simple closed curve C in R2, then this curve partitions the rest of R2, right? Except the points of the curve, right? The points of the curve forms a subset. So if you remove this point, right? So it partitions the rest of R2 into two disjoint arcwise connected open sets. Okay. So again, these terms are technical, but what we want to say is that if you take the entire R2, just put one simple closed curve, right? Which a curve which does not intersect itself. Then it divides the region into two parts, right? One is the inside and one is the outside. The inside part is connected if the graph is simple. It is connected in the sense that you can find a curve connecting any 2 points of this area. It's an open set, and similarly the outside part is also have the same having the same property. So this is what Jordan curve theorem says, that it partitions the region into two parts. Now, if you come back to the embedding, you will see that you take the embedding of any given graph, then what you do is that you remove all the points of this embedding. That is the points that belongs to the curves representing the edges as well as the vertices. So if you remove all these points, then the region might have several connected, it gets in several connected components, right? So these connected parts of the region, the remaining parts, are called the faces of the graph. Okay? So intuitively, it is clear that if you look at a picture of the graph, right? So you look at this connected regions which you can find inside, right? They are all faces. For example, this is a face. This is another face. And then the outside part is also a face because it's also a connected region, which I call F1 here. So when you take any embedding of a planar graph on the plane, you can talk about the faces of the graph. So the faces of the graph are basically the external face, right? The outside face, where every point other than the other faces and the curves, and then the internal faces or bounded face, right? There is unbounded face, and there is also the other faces are all bounded. So again, this fact that you can define these faces is a consequence of the Jordan curve theorem. Now, here are a couple of more examples. If you look at the first graph, there is no cycle. Therefore, removing these points of the embedding does not create a disjoint set, right? I mean, there is only one set. They don't create several sets, right? So there is only one connected component. Therefore, that is the only face, which is the outer face or the unbounded external face. So that is the first example. In the second example, you will see that you have another graph with a very nice looking embedding, and you can see there are exactly three faces, right? So what are these three phases? The phase one is this the four edges from a cycle. Then you have another phase, bounded phase, which is F2 marked here, which is 1, 2, 3, 4, 5, 6, 7, 8 edges, right? Then the entire remaining part, is one connected area. So therefore, that forms a phase F3. Even though you have this weird shapes, all these areas are connected. Therefore, that entire part So it is the outer face only, right? It might look like internal part if you are not careful. In some certain drawings, you might think that like parts like this might look like internal face, but it could be external face. So you have to be careful, but one can look through the embedding clearly and carefully, and then you can see what are precisely the faces of the graph. Now, here I give you an example of a graph which I claim that it is not planar, that you cannot find an embedding on the plane where no edges cross each other. Okay, so this is the first graph, is the complete graph on 5 vertices, which is K5, and I claim that this graph is not planar. I welcome you to think why this is not planar, right? Or how do you prove a graph is not planar? Because to show a graph is planar, all you have to do is to come up with an embedding, right, where edges does not cross each other. To show a graph is planar is easy, in the sense that you just need to come up with one embedding. But now, if I ask you to prove a graph is not planar, then how will you do it? If you look at one embedding and say that, okay, here the edges cross, then I can say that, okay, that is not a proof, right? Because as I showed you before, you have this graph K4, right, where we saw that there is an embedding where the edges cross, but the graph is still planar, right? So showing me 10 different drawings and saying that, okay, none of these drawings are planar embeddings is not a proof that the graph itself is not planar. Right? So think about this, right? In this example, we saw that you have the complete graph on 4 vertices, but it also had a nice plane embedding, right? Now, can you come up with an argument to show that the graph is not planar? Here is another non-planar graph, which is the graph complete bipartite graph K33. So this complete bipartite graph K33 is also not planar. That is my claim. Okay. Again, try to draw this graph and make the embedding so that it is possible. Try to make it planar, or try to minimize the number of edge crossing and see where you are going to miss out. Okay. So if it is possible to do this, then it would be nice. And then another way to show is to think about proving how this is how to show this is non-planar. And I suggest that you can also try to use the ideas of Jordan curve theorem. So how do you prove this using Jordan curve theorem? So that would be a nice exercise to think about. We will come to this later. Now, you have a homework question that try to embed the complete graph on the torus, okay, so that none of its faces are triangle. Okay? This is just an intellectual exercise. Try to see how you can come up with this. Okay, so what is a torus? Let me try to draw it. So this is a drawing of a torus that just to show that this is basically a cylinder that is connected together, right, at the endpoints, so that you get a medu vada shape object, right, or a donut shaped object. So this is basically a surface with a genus more than the genus of the sphere. Okay. So, like if you take a sphere, you take a sphere, and then you attach a handle, okay, like this. Then this topologically is equivalent to the torus. So basically, this is the number of handles tells you the genus, and the genus of the torus is 1. And you can have higher genus. And when you increase the genus, you will see that you will be able to put more and more edges without the need for crossing, right? Because the surface becomes more complicated, you can do more stuff like this. Now, the interesting part about this exercise is that if you look at the embedding of the planar graph, the K4 on the plane, right? The complete graph on forward, right, on the plane, all its faces are triangles, right? You look at any of these faces, right? Each face is basically a 3 cycle. The boundary of any face is a 3 cycle. Even the outer face, right? The boundary is a 3 cycle. But on the other hand, what I want you to do is to find an embedding, okay, on find an embedding on the torus for this graph so that no face is a triangle. Okay, this is probably not immediate, but if you think about it, you will be able to come up with an answer. Now, if you studied school geometry, you might have come across these objects, right? These are the Platonic solids. There are 5 regular polyhedron which are called Platonic solids, and these are the tetrahedron, right? That is the first one. The tetrahedron has 4 vertices, right, and 4 faces, and then 6 edges, right? You can verify that there are 6 edges, 4 vertices and 4 edges, 4 vertices and 4 faces, right? Now, the reason for the graph, right? The vertices of the graph, edges of the graph, and faces of the graph are called to be vertices, edges, and faces. Also has some thing to do with these shapes. Okay? So you have this Platonic solids. First one is tetrahedron. Second one is cube, right? Which is we are all familiar with. It has 8 vertices, 12 edges, and 6 faces. Then you have the octahedron, right? And each face of the cube is basically a square. And you have the octahedron, where you have triangular faces again. You have 8 faces, then you have 12 edges, and you have 6 vertices. Then you have the icosahedron, right, which has how many faces? 1, 2, 3, 4, 5 plus 5 plus 10, right? So 20 faces. It has 12 vertices, I think. 5 plus 5 plus 2, 12 vertices. And then you have how many edges you have? Like you have 5, yeah. 5 plus 5 plus yeah, yeah. So we already counted that, right? No, 5 plus 5 plus 5 plus 5, that is 20 plus 10, right? 30, 30 edges, right? Am I right? 30 edges, 10 and how many? 20, 5 plus 5 plus 20 faces. So 20 faces, 20 faces plus 12. Yeah, exactly. Yeah, so you have 30. Now then you have the dodecahedron, which has pentagonal faces, and then it has how many? 1, 2, then 1, 2, 3, 4, 2, 3, 4, 5, 5 plus 5 plus 10 plus 12 faces, and then it has 30 edges. Okay? So these are the Platonic solids. Now, if you look at this more carefully, you will see that the number of faces of the cube is the number of vertices of the octahedron, and the number of faces of the octahedron and the number of vertices of the cube are also the same, right? Similarly, if you look at the icosahedron and dodecahedron, again the number of faces in one becomes the number of vertices in the other, and vice versa. And then tetrahedron stands alone, and but if you can try to connect between find a connection between the cube and octahedron, or the icosahedron and dodecahedron, the same relation holds for tetrahedron with itself. So this is a kind of what's called duality. We will not go into duality in this course, but it may be nice to think about this. But we will see something very nice about this, and there is a relation between the vertices, edges, and faces, which was proved by Euler, Leonhard Euler, and that has been generalized to planar graph as well. So we will see what is this relation. So let's look at the tetrahedron case. So it has 4 vertices, 6 edges, and 4 faces. Right? Let us observe that the number of vertices, right, which is 4, plus number of faces, which is 4, is equal to number of edges 6 plus 2. Now, if you take the cube also, you will see that number of vertices, which is 8, plus number of faces, which is 6, is equal to 14, which is 12 plus 2, which is the number of edges plus 2. Right? Similarly, you will see the same thing holds for the octahedron, icosahedron, and dodecahedron. Right? So verify this, and then take any graph, right? So take a planar graph, look at the embedding, right? And look at the number of faces, right? If you take any graph like this, it has 8 vertices, right? 1, 2, 3, 4, 5, 6, 7, 8. Then it has 9 edges, 4 plus 4 plus 1, and exactly 3 faces, 1, 2, and 3. And 8 plus 3, right? The number of edges plus 3 is actually equal to the number of vertices plus number of faces. It's actually equal to number of edges plus 2. Take any other planar graph, for example, the one below. You have 13 vertices, 18 edges, and 7 faces, right? And again, 13 plus 7 is equal to 18 plus 2. So this is easy to see. Now this identity is called Euler identity because Euler proved this for the polyhedron. Right? He observed it and showed this. And it has been generalized to graphs later. And it's called Euler identity. So let G be a connected plane graph. Okay? Plane graph means that it comes with an embedding. Right? Because without the embedding, you cannot talk about the set of faces. So we talk about plane graph when you have the planar graph with a fixed embedding. So let G be a connected plane graph. Okay? So we'll assume the graph is connected. Then the following identity holds. That is the number of vertices of the graph plus number of faces of the embedding is equal to the number of edges plus 2. So again, examples. So if you take any tree, there is no cycle. There is only one face. Right? The number of vertices is 6. Number of edges is 5. Right? And that's it. So you have the identity. Similarly, you take any other graph. You have number of vertices 7 here. Number of faces is 4. And then you have number of edges to be 9. So this is the identity. Now we want to prove this. So how will you prove this? So try to see if you can come up with a proof for this by yourself. If not, proceed further. Okay. So here is the proof. So we use induction on the number of phases. There are several ways to prove this. We want to prove it by induction on the number of phases. So if the number of phases is equal to 1, right? So when is the number of phases equal to 1 for an embedding on the plane? Only if there are no cycles. Because if there is a cycle, the cycle already separates the region into at least 2 parts, right? So therefore, when the phases are equal to 1, then you cannot have several, you cannot have any cycles. So therefore, the graph is acyclic. And since we are assuming the graph to be connected, the graph must be a tree, right? So when the graph is a tree, the claim is that the identity always holds. So can you tell me why? Okay. So think about this and see why the identity holds if the graph is a tree. Okay. The identity that number of vertices plus number of faces is equal to number of edges plus 2. Because we already know that for a tree, the number of edges is equal to number of vertices minus 1. Right? Number of edges is equal to number of vertices minus 1. So therefore, number of vertices plus the number of faces, which is equal to 1, is actually equal to number of edges plus 2, because number of edges is number of vertices minus 1, right? So that is the proof. Hence, we have the base case, right? So once we have the base case, we can assume the result holds for all planar graphs where the number of faces is less than k, for some k greater than 1, right? So assume that the result holds for connected plane graphs with k greater than 1 phases. Now, let us take any graph, right, with more than let's say k phases, right? So take any graph with more than k phases, k plus 1 phases, and then we will use the induction, right? So how do you do that? So again, maybe it is going to be illuminating if you think about this for a few minutes and see, can you solve now this by induction, right? Can you complete the proof by induction? So I will let you think for a few minutes and then pause the bar, right, video, and then continue after spending some time thinking about this. Okay. So what we will do is that we will assume that the graph has k greater than 1 phases, and then we will consider the cycles in this graph, right? Because if there is no cycle, we know that there is only one phase. So take any phase, right? Any phase boundary, right, of the bounded phase, right? Any phase boundary is going to be a cycle, right? So take the phase boundary of any bounded phase, for example, the A, B, C, D phase here, right, in this graph. If you look at this particular phase, it has 4 edges, right, in the boundary, right? And now take any one of the edges that you want, right? You take any one of the edges that you want, and then what you do is that you look at this particular edge, right? So if you take the edges in the boundary of a cycle, that edge separates exactly 2 phases, right? That is what you should see, right? If you take any edge, right, no matter which edge is that, if it is in the boundary of a cycle, right, of the phase, then that edge belongs to exactly 2 phases. The phase which is one of the internal phases, right, and then the one which is the external phase in this case, right? And if you take, for example, the other edge, right, this one, then it separates 2 regions, right? Again, 2 phases, and these 2 phases are not joined by, in the embedding, right? If you remove the points of the embedding, then these are disconnected components in the R minus the graph, right? So if you look at these components, they are basically separated by this edge, and this edge belongs to exactly 2 phases, right, in the boundary of exactly 2 phases. So we have this observation, right? Now, what happens if I remove this one edge from the graph, right? So look at the graph G minus this edge E. If I remove the edge from the graph, then, right, I have removed, let's say, CD, the edge CD. So if I remove CD from the graph, then the edge which was separating these 2 regions is no more present, and therefore these 2 regions gets connected into a single region, right? This entire area becomes one single region, right? So what happens with the number of phases in the graph when I remove one edge in the boundary of a cycle? The number of phases decreases by exactly 1, right? Because 2 phases has been merged into 1 phase, and nothing else happened to other phases. And therefore, I get a graph with 1 less number of phases, right? Now, if the number of phases is strictly less, I can use induction now, right? So I use induction because by induction hypothesis, anything less than k, right, the result holds, and therefore, I started with a graph with exactly k phases, and now I have removed one edge. The new graph has exactly k minus 1 phases. So therefore, I can use induction. Okay. So how do I use induction? Now if you look at the the cycle, right? So here is a formally written down argument. So CB any cycle, right, and EB any edge of the cycle, right? So the edge G lies on the boundary of exactly 2 distinct phases, and deleting the edge E, right? These 2 phases gets connected and merged into a single phase. Now the graph G minus E is connected, and can you tell me why? Right. So the claim is that after removing the edge, the graph is still connected. Right? This is not necessarily true always, but in this particular case, I claim that the graph G minus E is connected. So again, pause the video and think for a few minutes before continuing. Now, the graph G minus E is connected because E was part of a cycle, right? So if I remove one edge from part of one cycle, then it is not going to disconnect the graph. Again, you can formally prove this using the arguments that we have studied before. And once you have this, it is easy, right? You have a graph which is connected and the number of faces is less. So therefore, by induction hypothesis, it satisfies the Euler identity, right? So therefore, for the graph G minus E, the number of vertices in G minus E plus number of faces in G minus E must be equal to the number of edges in G minus E plus 2. Right? So the Euler identity holds, right? Now, what we know is that the number of faces is exactly, right, 1 less than the number of faces in G, right? So this equation is true. Number of edges also has decreased exactly by 1, right? That's how I got G minus E, deleted exactly 1 edge. But what happened to the number of vertices? It remains the same. Now, if you look at the earlier identity, the number of vertices in G minus E is equal to the number of vertices in G, right? This is actually equal to the number of edges in G. On the other hand, I subtracted exactly 1 from the one term in the left side and exactly one term from the one term in the right hand side. So the identity remains the same. Right? So therefore, cardinality of V of G plus cardinality of F of G, right? The number of faces of G equal to number of edges in G plus 2. Right? This also holds. So I just added or subtracted, whichever way you want to look at, 1 from both sides of the identity. So therefore, we have the proof of Euler identity. So for any connected plane graph, right, the number of vertices plus number of faces equal to the number of edges plus 2. Now, you can ask what happens when the graph is not connected. Okay? So I leave it as an exercise for you to figure out what happens if the graph has several components. Now, here is a corollary. Okay? So let G be planar, right? In every embedding of the graph G on the plane, the number of faces remains the same. Right? You can have several embeddings of the graph, right? But for example, I will show you, the graph with the different embeddings. Let us take one example. So let us look at this graph, right? This was this embedding. It's a planar graph, right? With a plane embedding. Now look at another embedding of the same graph. Now this is a different embedding of the graph because if you look at the if you look at the cycles, right, of the phase length, right? So look at the length of the phases in this embedding, right? You have a 3 cycle here, there is a 3 cycle here, there is a 4 cycle here, and then there is a 6 cycle boundary on the outer phase. But on the other hand, in this embedding, you have the phases have length 3, then 1, 2, 3, 4, 5, right? And again, the boundary of this phase is 5, right? Here it was 3, 3, 4 and 6, right? So the embedding is different, right? So the embeddings are different, but then you can have several possibilities for different graphs. But in no matter what, this earlier theorem tells you that the number of faces in the plane or embedding must always be the same, because the identity, right, says that the number of vertices plus number of edges, number of faces is equal to number of edges plus 2. Right? So therefore, since all the other parameters are the same, right, number of vertices and number of edges remain the same, it must also follow that the number of faces remain the same. It's a direct corollary of the result. Now here is a nice homework question, right? Let G be a planar graph with k components. Generalize the Euler identity satisfied by this graph, right? So the Euler identity for a graph with several components will be slightly different from the Euler identity for a connected graph. So can you find out this identity? So this is a nice homework. Now, using this Euler identity, we can prove several interesting results. Okay? So it's a very powerful tool actually. And what we are going to do with this, first is to prove that the planar graphs cannot have too many edges. So if you recall graphs, right, an arbitrary graph, right, for example, if you take the complete graph on n vertices, you can have n choose 2 edges, right, n into n minus 1 by 2, right? It's like close to n square by 2, right? So you have many edges possible in a graph. On the other hand, one can prove that if a graph is planar, you cannot have too many edges for this graph, right? So if the number of vertices is fixed, then the number of edges is bounded by a factor. Now, how do you prove this, and why is this the case, right? So an intuitive way to look at this, why the number of edges is small, is that when you have an embedding, right, the faces, the boundaries of the faces must all have this edges, right, that define the boundary of the face. But now, if you take any face, right, the face boundary has at least 3 edges, right? For any face to be defined, you need at least 3 edges because you need cycles to define. Now, this says that, like, when the when you have a certain number of faces, then the number of edges must be related to the number of faces, right? Because you have the Euler identity which says that number of vertices plus number of edges, number of faces is equal to number of edges plus 2, right? So since every face has at least 3 edges to be in the boundary, right, this puts a restriction on the number of edges. Now, we want to use this idea, right, to prove formally that the number of edges in any planar graph is at most 3 times the number of vertices minus 6 for n at least 3. For n is equal to 2, you have this obvious counterexample, right? The trivial case where you have 2 vertices, 1 edge, right, where the identity is slightly violated. So if n is at least 3, then we have the number of edges in the planar graph is at most 3 times the number of vertices minus 6. So the proof uses the observation that every face boundary has at least 3 edges. So what do we do? So we consider an embedding of the graph G, and we suppose that the graph has let's say n vertices, and the number of edges is denoted by m, and number of faces denoted by f. So the graph has n vertices, m edges, and f faces. So what we need to prove is that m is less than or equal to 3n minus 6. Okay, so first of all, we observe that if the number of vertices is actually equal to 3, right? Then the number of edges possible, right, is also at most 3, because even the complete graph on 3 vertices can have only 3 edges, right? And for n equal to 3, the identity is clearly true, right? So therefore, because 3 into 3, 9 minus 6 is actually equal to 3. So therefore, 3n minus 6, m is at most 3n minus 6. Now, therefore, we will assume that n is at least 4, because the case 3 is done, right? So let us start with the assumption that we have at least 4 vertices, and we have the identity, right? Euler identity says that the number n, right, n number of vertices n plus number of edges f, n plus f, is equal to m minus 2, right? Number of vertices plus is the number of edges plus 2, is actually plus, right? Number of vertices plus number of edges equal to number of edges plus 2. Now, since there are f faces, right, n plus f, right, and f faces, let us call these faces by name, right? f1, f2, etc., ff be the faces of the graph. Now, since each phase boundary, right, must have at least 3 edges, we know that 3 times the number of faces, 3 times f, will be less than or equal to summation over all the faces, the length of the faces, right? Length of the face is the number of edges in the boundary of it, right? So that is the denoted by mod fi, right? So summation I equal to 1 to f, length of fi will be for each fi it is at least 3, therefore it will be greater than or equal to 3 times f, right? But now, what we know about the relation between the faces of a graph and the edges is that if you look at the boundaries of faces, right, every edge, right, is incident to at most 2 faces, right? So a phase, an edge cannot be contributed or counted by more than 2 faces, right? So in the summation, an edge is only counted at most 2 times. So therefore, if you look at length of the boundary of a face is basically the number of edges. So therefore, you will see that since an edge cannot be counted more than twice, summation fi is less than or equal to 2 times m, right? Twice the number of edges. So summation fi is less than or equal to 2m. So now we have the identity 3 times f, right? 3 times the number of faces is less than or equal to 2 times m, which is the number of edges. We can now substitute this into the Euler identity, right? So Euler identity n plus f is equal to m plus 2. So substitute it here, right? So we have 3 times f less than or equal to 2 times m, and 3 times, now if you multiply by 3 on the Euler identity, you will get 3 times f is equal to 3 times m minus n plus 2, right? Because f is equal to m minus n plus 2. So, which is less than or equal to 2 times n, right? So now we get a relation between m and n because transferring m to the left and a number of vertices to the right, you will get that 3m minus 2m, which is m, less than or equal to 3n minus 6. Right? This is the identity that we were looking for. So for any planar graph, G, we have shown that you can have at most 3n minus 6 edges. Now we use the identity because we can assume that the graph is connected, because if the graph is not connected, right, what we can do, we can add edges to make it connected, right? We can add edges to make it connected, and which will only increase the number of edges, right? So even after adding edges to make it connected, we have the identity. Therefore, for any planar graph, we will see that the identity holds true. Okay, so by proving it for connected graph, we could generalize to other graph. So for arbitrarily planar graphs, now we have the identity. We can now use this to prove several results, right? This idea, right? So so one way you can immediately think of using this theorem is that if a graph is given to you, right, and you are asked to check whether the graph is planar, all you have to the first thing that you can do is to check if the number of edges is more than 3n minus 6, because if the number of edges is more than 3n minus 6, you know immediately that the graph is not planar, right? Because by this result, we know that any planar graph will have at most 3n minus 6. So this can be used to prove some interesting results. So here is a homework. Prove that if G is a planar graph, then G contains a vertex of degree less than or equal to 5. So think of this and try to come up with that. So now we have the tool to prove that the graph K5 is not planar, right? So so we have these two non-planar graphs that I introduced to you earlier, right? And I claim that these two graphs are not planar, right? And we did not prove it. Now we can prove it by using the Euler identity. So let us prove the first one. K5 is not planar. So K5 case is very easy. K5 has 5 edges and 10 edges, right? So in our Euler identity form, n is equal to 5, m is equal to 10, right? And now 3n minus 6 is 3 into n, which is 3 into 5, 15 minus 6, which is 9, which is less than 10, right? Which is the number of edges in the graph, right? So since you have more edges than 3n minus 6, the graph is definitely not planar by Euler identity, right? Using Euler identity, we are able to prove this number of edges bound. So the graph is immediately not planar, right? K5 is not planar. Now let's try to apply the same for K33, right? So we have K33, the graph K33 is not planar, right? So let us try to use the same idea. K33 has 6 vertices and 9 edges, right? And what is 3n minus 6, which is 18 minus 6, which is 12. But the graph on 6 vertices allow 12 edges to be, right, there, at most. But we have only 9 edges, right, in the graph K33. So the identity does not tell us whether the graph is planar or not, because the the result that the planar graph can have at most 3n minus 6 edges is a one-directional result, right? It does not tell that if the number of edges is less, the graph is planar. It only tells that if the number of edges is more, then the graph is definitely not planar. So using this idea immediately is not helping, right? Directly we cannot use this bound to count to show whether the graph K33 is planar or not. Now how do you go about proving K33 is not planar, right? So obviously the number of edges is not going to help, or directly by using this formula. Can you think of something about K33 and how you can improve upon this? Okay, so think about this for some time. and then we will look at the proof. Okay, here is a different approach, right? So you have the graph K33, but the K33 is a bipartite graph, right? It's a complete bipartite graph. Now, a bipartite graph has no odd length cycle, so therefore K33 has no 3 cycles. Right? So when we were trying to prove this, a relation between the number of vertices and edges, we use the fact that every phase boundary has at least 3 edges, right? But now, since the graph is bipartite, you know that any phase boundary must have at least 4 edges. So can we use this idea now to improve upon the number of edges itself, right? So let us take a bipartite planar graph. We know that if it has f phases, then every phase boundary has at least 4 edges, and therefore 4 times f is less than or equal to again 2 times f, right? By the same idea, right? Because if you sum over all the cardinalities of phases, each phase boundary has at least 4, but each edge is counted at most twice. So therefore 4f is less than or equal to 2 times n. Now directly using Euler identity, 4 times m minus n plus 2, which is f, right, is less than or equal to 2m. And this tells you that 2m is less than or equal to 4n minus 8, or m is less than or equal to 2n minus 4. Which is to say that any planar bipartite graph, right? We did not use its K33 or anything, right? Any planar bipartite graph has at most 2n minus 4 edges, right? So any planar graph has at most 3n minus 6 edges, but any planar bipartite graph has at most 2n minus 4 edges. Now this is a much improved bound for the number of edges. So therefore, let us try to use it on K33, right? So K33 has is bipartite, and 2n minus 4 for this graph is 2 into 6 minus 4, which is 8, right? But we have 9 edges in K33. So therefore, bipartite planar graph cannot have these many edges, and this tells you that K33 is not planar. So this way, you can use Euler identity in several forms, right? And with more improvements to show several results about planarity. So here is a result that you should remember. We proved one theorem in between, right? As part of proving attempt, we proved another theorem, which is that a planar bipartite graph has at most 2n minus 4 edges. So keep that also in mind.